Hello everyone, I'm KyeongMin Kim, a master student at the IXL Lab. Let's begin the seminar on toward Unstructured Unlabeled Optical Mocap, a video help. This is the demo video of the paper. To put it simply, it involves using both image and marker data for motion capture. Motion capture, as known as mocap, is converting real-world actions into data. It is mainly divided into three methods. One method is marker-based optical motion capture. This method involves calculating the pose by tracking the 3D positions of markers using multiple infrared cameras. Its pro is extremely accurate and is considered very expensive and challenging to set up the environment. The second method is markerless motion capture. This method involves performing object detection from images followed by predicting the human pose and shape. It supposes that only one camera is needed, but the cons is that the 3D positions of the joints are inaccurate and weak to occlusion. The last one is IMU-based motion capture. This method uses inertial sensors attached to the joints to measure the velocity of the joints. Its processor moderate cost and not affected by lighting conditions, but the cons is that affected by magnetic fields and prone to noise. Marker-based optical motion capture is still considered the golden standard due to its accuracy, but the others use both marker-based optical motion capture and markerless motion capture. It is the reason that they use both marker-based and markerless motion capture. When only using marker-based motion capture, predicting pose is difficult without a marker layout. The marker layout is as follows. It provides information on where the markers were placed on the body during motion capture. When only using markerless motion capture, there is relatively more noise and some frames may need to be completely discarded. However, if both data types are used together, like motion capture data, marker data and video data, we can easily obtain the marker layout from marker-based mocap by retrieving the SNPL mesh from the markerless mocap. Additionally, partial body reconstruction, which was previously impossible, become achievable. Now it's time to explain the method. First, SNPL parameters are extracted from the monocular video. In this test, HMR2 is used. HMR2 is the state-of-the-art of the predicting human pose and shape estimation from the monocular video. The paper name of HMR2 is Humans in 4D Reconstructing and Tracking Humans with Transformers. And the SNPL is Parametric Human Body Model. The parameters consist of body pose and betas and global translation. Body pose is the joint rotation and betas represent the body shape with 10 float values. With the inertial SNPL parameters estimated from the monocular video in the previous module, intuitively, one can optimize this SNPL model by fitting it to the markers. However, directly solving the optimization problem can easily get stuck to bad local minima. So, the process is divided into two steps. In the marker segmentation step, markers are grouped based on their distance relations across time. If the distance between markers remains similar throughout all sequence, they are grouped together, like this, and like this. This leverages the fact that markers belonging to the same bone maintain relatively constant distance relationships. And in the part localization step, segments are matched by calculating the chamfer distance between the vertices of specific SMPL parts and the markers. Chamfer distance is a loss function used to measure the difference between two different point clouds. A smaller chamfer distance indicates the higher correlation between the two point clouds. In this case, the segmented markers and the vertices connected to the single bone, each from a point cloud. Mocap solving is consisted of 5 stages. It's my mistake. It's not finding rotation, it's setting root rotation. In stage 1, root rotation is set up in 0 and 90 and 180 and 270 as initial values. The stage 2 is force fitting, and the root rotation is optimized from the initial values independently. 0 and 90 and 180 and 270 and each root rotation optimized. In stage 3, it called by marker vertex correspondence. In this stage, it finds the vertex of the optimized SMPL mesh with the closest average distance to marker over the entire sequence. This process may seem similar to part localization, but in part localization, the goal is to identify the bone to which a marker group belongs. In stage 3, however, the objective is to find the closest vertex for each marker. The closest vertex of this marker is this, and the closest point of this marker is this. The stage 4 is inverse kinematics. In stage 4, pose, shape, and mesh are optimized to achieve a distance of 9.5 mm between the vertexes and markers. And the stage 5 solver refinement. In stage 5, the stages 3 and 4 is repeated. It is the entire pipeline. Firstly, when the video and marker data are received, initial SMPL parameters are extracted from the video. In this stage, after that, and the markers are segmented. After that, part localization is performed using the initial SMPL parameters. Next, the process goes through pose fitting and marker vertex corresponding and inverse kinematics and repeated to solve the pose. It is evaluation result. They evaluate about M2S and MPJV and MPJV and V2V. M2S is distance between marker to surface. It is best when 9.5. And MPJV is mean per joint position error, and MPJV is mean per joint velocity error. And MPJV evaluate the temporal consistency of a motion. V2V is vertex to vertex, and it measures body shape and pose. They also conducted evaluation on other studies when video data was provided. HMR2 is, however, is video-only method, so global position, orientation, and scales are ambiguous. so it was aligned to ground truth. V-poser and humors are sensitive to having strong initialization, so it is initialized with HTML2 SMPL parameters. They said that it showed good performance in most cases. Here is the visualization of the result on the Moyo dataset. Moyo dataset is challenging that has unique and difficult poses. However, they demonstrate that their approaches perform well on the dataset as well, claiming that it can be applied to unique and challenging poses. It is a limitation that mentioned in paper. It sometimes struggles with aligning the correct parts to markers, especially when they lack certain identifiable characteristics. For example, if an actor only has markers on the left leg and jumped with both legs, then the wrong leg could be aligned to the markers. Another issue is that very sparse layout can be labeled incorrectly due to poor coverage. Next is limitations that are not mentioned in paper. When I watched the demo video, the markers appear to have no noise. It is too clear. The paper mentioned that if tracking of markers across time is possible during the marker part matching process, marker to marker correspondence can be obtained. However, in actual motion capture scenarios, marker tracking is often interrupted due to noise. I am uncertain whether this method can only be used after marker noise removal is fully completed. Yes. Thanks.